For our next problem, again, it looks like a normal system of equations, so we're going to go ahead and get the augmented matrix. 5, negative 3, 1, 1, 1, negative 2, 3, 3, 4, negative 3, 2, 2. I want a 1 up in the upper left-hand corner. So in order to get the 1 there, because it's the first step, I could do something clever. Look at any other elements in the column and see if I have a 1 that's already there, and I do. So if I could just take row 1 and interchange it with row 2, that will get me the 1 very quickly. Notice that row 3 is not changing. And just my progress check, I have a 1 there. Next I want a 0 below. I have 2 elements there that I need to take care of, so I'm going to use both of those in the same step. So on the first one, I'm trying to get a 5 to become a 0. Using the rule to get a 0, I'm going to take the opposite of the number, negative 5, times it by the row with the 1 in it. In this case, the row with the 1 in it is row 1, and add it back to the row 2. At the same time, I'm trying to get the 4 to become a 0, so I take the opposite sign, which is negative 4, times it by the row with a 1 in it, and add it back to row 3, put it into row 3. On my next matrix, notice that row 1 stays the same, so I'm going to go ahead and put that in first. Then I'm going to do the work for the second row off to the side. I'll do this one vertically, negative 5 times row 1 plus row 2. So if I take negative 5 times row 1, that gets me negative 5, positive 10, negative 15, negative 15. Add it to row 2, which is 5, negative 3, 1 and 1. When I add down, I'm getting 0, 7, negative 14, negative 14. For the green one, I'll do that one horizontally. So I have negative 4 times row 1 plus row 3. Now as I'm doing it 2 different ways, by now hopefully you've decided which way you like better, and you should just do it your way on both and see if you can't get the right answer. Negative 4 plus 4 is 0. 8 minus 3 is 5. Negative 12 plus 2 is negative 10. Negative 12 plus 2 is negative 10. So that gets me 0, 5, negative 10, negative 10. All right, let's do a little progress report. I got a 1, check. I got a 0 below it, check, check. Next, I want a 1 where the 7 is. So when I go back to the rules to try to find out how to get a 1, because I can't interchange it with another row, there's nothing convenient there. What I can do is I can take the reciprocal of 7, which is 1/7, times it by row 2, and put it back into row 2. Notice that the first and third row stay the same. I like to put those in first so I don't forget them. And then I'm going to take the middle row times 1/7. Or if you want to think about it as divide by 7, that's fine. You just can't write it divide by 7 because there's no such thing as matrix division. So 0 divided by 7 is 0. 7 divided by 7 is 1. Negative 14 divided by 7 is negative 2. Negative 14 divided by 7 is negative 2. All right. So checking on my progress, I have 1 and 0s below it. Check, check. I have a 1, and now I want a 0 below the second one. So in order to get a 0 there, looking at the steps to get a 0, I would take the opposite of positive 5, which is negative 5, times the row with the 1 in it. In this case, the row with the 1 in it is row 2, and add it back to the row we're manipulating. So the row we're changing here is row 3, which means row 1 and row 2 stay the same. And then I'll come do the work off to the side. You do your work the way you like it. Negative 5 times row 2 gets me 0, negative 5, positive 10, positive 10. Row 3, I have 0, positive 5, negative 10, negative 10. When I add down, I get 0, and I get 0. That's what I was hoping to get, but accidentally I also get zeros on everything else. This is not my fault. I did not make a mistake. It just happened that way. So looking at my progress, I have a 1, I have the zeros below. I have a 1, I have a 0 below. If you're ever zeroing out that third row accidentally, you know you have a special case. In this case, because 0 equals 0, I have an infinitely many case. So I'm going to go ahead and rewrite the equations. Because I have 0 equals 0, which is a true statement, that means I have an infinitely many solutions. But I can't just write infinitely many. That's actually not sufficient. What I have to do is I have to tell you what the solutions are. So I'm going to solve for x by moving the 2y over. So that's positive 2y minus 3. I forgot a z right there. I should have had a plus 3z. So when I move it over, it's a minus 3z plus 3. On the second equation, I have y equals, move the 2z over, and positive 2z minus 2. And then for the third one, I don't have an equation. So what I'm going to do is I'm going to let z equal some variable. The variable I choose is t. You could use whatever variable that you like. So I already have t as my third part of my ordered triple. To solve for y, I'm going to plug in z, which is t, into my equation for y equals, which gets me 2t minus 2. And then I'm going to plug in both y and z into my blue x equation. So 2 times y, but y is 2t minus 2, minus 3 times z, but z is now t. When I distribute, I'm getting 4t minus 4 minus 3t plus 3, which reduces to x equals 4t minus 3t is 1t. Negative 4 plus 3 is negative 1. So I get t minus 1. This is the solution for an infinitely many solutions answer to a system of equations in 3 variables. This represents every single solution that truly works. It's not just that every solution works, but this tells you which of the solutions do work, even though there's an infinitely many, where t is any real number. For example, I could plug in t is 7 or t is negative 3 halves. Whatever t I pick, I can get an ordered triple, which is a solution to the system of linear equations in 3 variables. And this concludes our lesson on more matrices and special cases of matrices.